Okay, so we're going to finish this day 1 part on number 5, so make sure in your packet your page looks like mine now. Actually, this function right here, this graph, is on 2 different pages. All right, we're going to look at it 2 times. So on this first time, we have the function, we have the graph. Notice that what we don't have is the table. All right, but if you have an equation, could you create your own table?
Yes.
Of course you could, right? And so when we're looking at this, when they give you the equation, they're going to tell you about how many subintervals you need. So if I want this to be broken up into 4, how long or how far or whatever is just one subinterval? Yeah, a half, right? So this is going to be 1, and it's going to be 0.5. I'm going to go ahead and draw the line down there, and so on. So basically every 2 blocks, but in this case, the base here is going to be 0.5. Now, it has to be the same. You can't switch it up and have the base be 0.5 and then something else. It's got to be equal subintervals. So remember when we're looking at this and we're trying to do our estimates of the area, yesterday we talked about a few different ways to do this. We have our lower and our upper estimates, which are extreme over and under estimations. We have averaging those 2, and we have a trapezoid. What was the correlation between the trapezoidal sum and averaging the upper and lower?
The same.
They're the same, okay? So let's go ahead and do this whole left. Now, I'm telling you on this one that it's lower and left. So how could you know by looking at this that if I picked the left point instead of the right point, that it would be a lower or underestimate? How would you describe this function? It is increasing. Therefore, the left point is always going to be lower or smaller or whatever than the right point. And so when we're kind of doing these rectangles, again, we're not going to do trapezoids on this one. When we're doing the rectangles, we pick the left point to determine the height of the rectangle, and I can see clearly that this is an underestimation. So let's just review this. The first rectangle, 0.5 times the height would be 0. So that's extreme underestimation because it's saying there's nothing there. All right. Now, we used to look at the table to figure out the height, the y value. We don't have that here. So what you're going to have to do is use your function. I'm going to encourage you to use your calculator here, but you can do this several different ways. You can plug in 0.5 and do 0.5 squared plus 0.5. You can plug this into y1 and go look it up on the table. You can even store values, like store the value in for x and then type out x squared plus x. However you want to do it, I want to know when x is 0.5, what's the y value? And it should be somewhere between 0 and 1. That would be reasonable. So you're going to want to use your calculator on this. If you don't have your calculator, you get to do it by hand. Or use your phone. Because all we're doing is crunching numbers here. So as soon as you get it, shout it out.
Function at the top.
Yeah.
Top right.
0.75.
It's not that cool. Oh, yeah.
I would use, instead of using this, because it kind of looks weird, I would just use what they say after the X's in the paragraph. 0.75, I heard. That is correct. And so our second area would be 0.75. That would be the height of this next rectangle, and the width would still be 0.5. And so we look at it like that, okay? And what about when you plug 1 in? You could do this without a calculator. You get 2. So that's going to be 0.5 times 2. And that's the area of that rectangle. So then our last one, again, is not a whole number, so you're going to have to plug it in. Get 1.5 squared plus 1.5. 3.75. So 0.5 times 3.75. And this is just like what we did yesterday. Okay, another way you could have written this is you could have just said 0.5 times all these heights. Right? We know that the base has to stay the same, so you could have done it this way, and this is going to give you the same answer. They mean the same thing, okay? In other words. All right, so let's type that in. And this is going to be our extreme underestimate. I'm going to turn off my email. See if my memory serves me. 3.25? Sure. Can you all get that? So 3.25 is that area right there that I've shown here in red. And that's an extreme underestimate. You see how this graph is very concave up, if that's even a word, very concave. It's extremely curved, so the little curves are going to make a bigger difference. The flatter it is, the less we'll be off right here. So now what we need to do is talk about our upper estimate. And again, this is just review of what we've already done, except instead of a table, I'm giving you the equation. Now don't reinvent the wheel here. Okay, if I'm talking about the overestimate, all right, what was happening in the second rectangle is now happening in the first. Likewise, the third rectangle is now just like the second one, and so on. So I can kind of look at my work and make life easier on myself. Now you are going to have to find the y value. And what happens when you plug 2 into the function? What's the y value? What's 2 squared plus 2? 6. Okay, so our upper estimate, I'm going to go ahead and just do the 0.5. Notice what all I'm really doing is taking out 0, and I'm putting a 6 in at the end. And I believe you get 6.25. All right, so the real answer, the true answer of what that area is underneath is somewhere between 3.5 and 6.25. Yesterday, the best we came up with was to average these two. And we said that still really wasn't the best answer. And so let's go ahead and do that. 3.25 plus 6.25 divided by 2. 4.75. Okay. If I did a trapezoidal sum, what would I get?
4.75.
4.75. Okay. Still though, this is not the exact answer because these are curves and not lines. So the question now is this 4.75, is this answer too big or too small? Is it an overestimation or underestimation? It's over, so it's too big. Why? Because f of x is concave up. Now, I didn't really ask you to do this yesterday, but how can you prove to me using calculus that f of x is concave up? The second derivative, okay? So if f of x is x squared plus x, what's f prime of x? 2x plus 1. And so what's f double prime of x? 2. Specifically, it's positive 2. Look, the second derivative is always positive 2, therefore it's always positive, therefore f of x is always concave up. Now remember when we had, and I want to make sure everybody gets this, and I'm going to make an extreme concave up little trapezoid here just to see, so we can see it. I really want that area. But when I am doing the trapezoid, which I know I didn't do here, but we still would have got the same answer, I'm putting in a little too much. And the steeper the curve, the more we have the error. So if you had to guess what the true answer is to this problem, okay, magically we could do this. What would you guess the true answer is?
4.25.
Between 4.4 and 3.2.
Yeah, it's definitely going to be bigger than 3.25. and it's going to be smaller than 4.75. It's going to be, though, pretty close to 4.75. It's not going to be like, it's not going to be like 4, okay? This is still a pretty good approximation, but it's a little bit too big. So I'm thinking like maybe 4.7, 4.6, something like this, okay? So I'm going to show you a different approximation. All right, so I want you to turn in your packet until you get to where it says the day 2. And if you notice, this problem is the exact problem that we just did. All right, except that the directions are just barely different. So the function's the same, interval's the same, but I see this thing called midpoint Riemann sum approximation. All right, midpoint means midpoint. Okay, let's go ahead and split up our graph the same way, because we need this to happen. But instead of doing left rectangles or right rectangles and averaging or doing trapezoids, we're going to do something different. So this is another type of Riemann sum. All right, the nice thing is the name tells you which one. All right, so what we're going to do is we're going to take the midpoint of the x's. So in this first subinterval, the x midpoint would be 0.25. And it's already listed there, so that's nice. We need to find, it's okay, just figure it out. All right, we need to find what the y value is. Now before we find it, I want to ask you, the x is the midpoint, like 0.25 is the midpoint of 0 and 0.5. Do you think this y value will be the exact halfway mark or midpoint of the two y values? All of you are saying that are saying something are saying no. Why not?
Well, you can see it's not, but it's also
okay, if this was a line, it would be.
right.
Line has a constant rate of change. Anytime you get into a curve and you have concavity, it's not going to be. So I'm going to prove to you, though, why it's not. Okay? So I want you to, again, take your calculator and you're plugging in 0.25 into this function. In other words, what is 0.25 squared plus 0.25? Yeah, 0.3125, right? That is not the average of my left and right endpoints. In other words, that's not the average of 0 and what was this, 0.75? If you average 0 and 0.75, you would get something close to this, but not exactly. You'll see?
0.5, sorry.
No, 0.5 is the x, but I'm talking about the y.
Oh yeah, that was 0.5.
Yeah. All right. So I'm going to do my rectangle, not in a sense averaging the two lower and upper estimates. What I'm going to do is just do my average at the beginning, okay? But it's not the average of the y's. It's using the average of the x's, in other words. So I'm going to really hammer down this word midpoint. The midpoint of the x will give you a new y value, and that's the height that we're going to use. And so let me draw the picture on this next one, and let me show you what happens. When I draw this, you can see that it takes up the majority of the space that we want. There's a little bit of overestimation right there, and then there's some underestimation over here. So it should kind of balance out. So before I move any further, do you think this is going to give me a more, less, or same accurate answer as the whole trapezoidal?
More.
We think more? Okay, let's see. Before we write anything down, I want you to go ahead and find the midpoints. Let's just do this all at one time. And what we're doing is we're trying to find the height of these rectangles, okay? And we're doing that by using the function. We're plugging in this x midpoint to find the y value. That then will be the height of the rectangle. And these are not going to be horrible numbers, but they're not nice numbers. Don't round. Don't ever round until the very end. You lose accuracy that way. Sure.
To do it the other way, can you just anti-derive and plug in 2?
When you say anti-derive, what do you mean?
Change the x squared to x cubed over 3.
Okay, so Crawford's already one step ahead of me. He's saying, can we take the antiderivative of this? And I'm going to show you all that in just a minute. I'm going to ask you questions about that. Yes, that's how we're going to be able to find the true answer. And the only reason I'm really harping on all this whole approximations is because it is on the AP test. And if you find the accurate answer, well, good for you. But unless you show that you know these approximations, you might lose some points. And sometimes we're not given the f of x, so it's not even possible. Next week, we're going to come back to this problem, find the exact answer, and kind of compare these numbers. But you're right. Okay. Who's got all these three numbers? Brett, can you tell them to me?
1.3125, 2.8125, and 4.825.
Okay, so when we add all these up, again, we can just do a single 0.5 times, then we add up all these numbers. Don't round until the very end. This is something you would need to show on the AP test. It's not good enough that you just labeled this picture and knew what to type in your calculator. You would have to show this step. So I'm not really requiring you to do anything that you're not later going to have to do. And we know our answer should be pretty close to what it was before, pretty close to 4.75. Anybody already found it?
4.625. 4.6.
So this is pretty close to 4.75. It's a little bit smaller, which we said it should be. And so far, this is seeming like this is more accurate than what we already have done. It could be, though, that it's too far over. Like, it could be that the true answer really is between this and then my earlier 4.75. We're going to answer that question next week. Before I talk any more about that, I want to show you the notation for this. Okay, integrating or antiderivative, we're going to use this symbol, all right, and we're going to say from 0 to 2. All right, that was the interval of the x's, the lower and upper bound of my x's. What you could see after this is f of x dx, or it could be where the actual function is written in like this. Okay? I do want you to notice that dx is in this, and that's because this thing is the derivative. Yeah, that's fine. X squared plus x is the derivative. So what we're essentially doing is going backwards. We're saying, what would be the equation so that when I take the derivative, I get this? And that's what Crawford was saying was, he said something about x cubed over 3. Because if you took the derivative of x cubed over 3, what would you get? You'd get x squared, right? The 3 would come down here. It'd cancel out with that 3. You'd be left with x squared. Anybody know what would be next? Someone else? X squared over 2. Now, do you think I could have something else? Yeah, so some of you have friends in Calc BC, or you're just smart like that. There could be some number here, which we're going to call C, because what's the derivative of a number? 0. All right? So this right here would be, what we were calling that capital F. That function before the function, okay? In other words, if our function is the derivative, then what came before it? And this is what all of chapter 4 is about. We're going to come up with stuff, and so Crawford is right. We're going to plug in 2, and we're going to plug in 0, and in this case, the 0 won't do much, but this is how we're going to find. So some of you, actually right now, you can kind of go and find out what the true accurate answer is. Okay, but I'm going to do that next week. All right, but this is good enough for now. All right, for the rest of this lesson, I want to talk about this AP test question right here. All right, 1998. How old were you in 1998? 2. Man, I graduated high school in 1998. But that doesn't make me feel old at all. All right, so here we go. This test, or this question was a long time ago, although this type of question is a very classic type of problem. I don't want you to think this stuff is not on the AP test. And when you look at this, a lot of it's going to look like physics. Again, there's a lot of overlap. So we have this graph. It talks about velocity in time. So I want you to see here that our y values are a rate, meaning they already gave us a derivative. What is the velocity a derivative of? Distance, right? What is velocity's derivative?
Speed.
Acceleration. We've already talked about these things. Okay, so they give us a picture of what's happening, and they give us a table so that if we need to use exact values, we have them right over here. We don't have to guess based off of the graph. So essentially what's happening here is imagine you're in your car, and you're, let's say, you're like stopped because you're at a stoplight or something. Okay, you've already been driving and everything. And then you start this timer, and 5 seconds later, after you've gone a little bit, you notice that you're going 12 feet per second. Okay. Is that very fast? For a car? No. If you look on the floor, these tiles are about 1 foot. They are exactly 1 foot, I shouldn't say that. So 12 of them in 1 second in a car really isn't that fast. Okay, and as time goes on, what are you doing in your car?
Accelerating.
You're accelerating. Your foot is pressing down on the gas. You're going faster and faster, and not in necessarily a consistent manner. What's your max speed? It might be easier to look right here. According to this table, 81 feet per second. Man, I can't stop coughing. Is 81 feet per second seem fast to you for a car?
Really?
We, in second period, I had somebody count the tiles, and there's like not quite 40 tiles in this room. So twice this room in 1 second. It is fast. So we're speeding along. You could definitely do the calculation to figure out what this is in miles per hour, but it's pretty fast. So maybe we see a policeman, or maybe the car in front of us is slowing us down, so we got to slow down. You're not necessarily pressing on the brake here. You could just be letting your foot off of the gas, and then, you know, the friction and everything could be, just the lack of gas could cause you to slow down a little bit, and then you speed up again. So maybe you pass the cop or something, and you're going to speed up again. I don't know. But that's what's happening here. All right, it's good that you have a picture of what's going on, because when they ask you questions, it's so easy to get acceleration, velocity, and distance mixed up. You got to keep them straight. So here, this is what we call a question stem. There's many things I could ask you from here. So A says, during what intervals of time is the acceleration of the car positive? And then I have to give a reason, and my reason better involve calculus. So when is the acceleration positive? 0 to what? 35. And then it's positive again from 45 to 50. Now I'm using parentheses. There are times when the AP test allows you to use parentheses or brackets, but the reason I'm using those parentheses is because of my reason. What's my reason?
Because F is not a prime post.
Well, okay.
Because the velocity is increasing.
The velocity is increasing, and at this point right here, we're not really increasing or decreasing, because what's the derivative at that max?
0.
0. So not positive. Acceleration would technically be 0 right there. So I'm going to say because v prime of t is greater than 0. All right, if you said velocity is increasing, yeah, you're right. Okay, but we're going to use calculus here. What is v prime representing? Acceleration. Okay, and it's representing the slope of these little segments. All right, so B says find the average acceleration of the car. Okay, this is where I'm going to kind of start writing stuff down here. When you see this word average, you should think AROC. Now, you write AROC on your test, good for you. Your test reader may have no idea. They probably could figure out what AROC means, but not every teacher uses this, okay? So I would write it so that you know what's going on, but you need to immediately think, do you need calculus to do AROC? Nope, you don't. That was the slope of which type of line? The secant line. So look, I'm given 2 endpoints. All right, so I got an endpoint over here, and I got an endpoint over here, and if I connect these two, that will give me the average acceleration. The slope of this line is the average acceleration. So I'm not doing derivative. Derivative would be the instantaneous acceleration or acceleration at one number. But this is going to be the average. And because acceleration is changing so much, putting just one number on it, you know, you kind of have to oversimplify. So this is what you got to do on this problem. You got to show this statement right here. V of 50 minus V of 0 is over or divided by 50 minus 0. Change in y or change in x. Notice the notation. On the AP test, you got to do this. It doesn't matter if you understand it and then you just write down the number because you did it in your head. You got to get the point. You got to show the average rate of change formula, so to speak. All right. V of 50 is 72. V of 0 is 0. And that, we don't have to write minus 0 again. That would be okay. But 72 divided by 50 turns out to be 1.4. And then what would my units be? Feet per second squared. There's 2 ways I know it has to be feet per second squared. First of all, velocity units are feet per second. Time units are seconds. So feet per second squared makes sense when you divide those 2 units. The other thing is this is average acceleration. And acceleration is always going to be like feet per second squared, miles per hour squared, something like that. Oh, yeah, they were nice, so nice to you. And on the AP test, if you don't put your units, you are most likely going to lose a point. I've seen it on the rubrics occasionally where they don't have that as a point, but usually it's its own point. And points here are valuable. I mean, you could do a whole lot of work and only get 1 point for that work, and then the units itself is just 1 point.
So would this be like a free response question?
Yeah, this is a free response question. And we're going to start to see more of these now that we've kind of built up what we know how to do. All right, I still need to kind of say what my answer means. All right, so I'm going to write this out. I'm going to say the average acceleration is 1.4 feet per second squared. And if I left this here, it's not really that, it's not good enough because I've left something out. Is this the average acceleration for all time? No. On the interval 0 to 50. So you could say on or at 0 to 50, and you could write this the way they wrote it, or you could write it in interval notation. Either way. But you'd have to write it somehow, okay? They want to see that you know what you're talking about. You got to prove what you're talking about all the time. Okay, so that's that. So really, both of these, we could, this is all stuff that we did in previous chapters. All right, C says, find one approximation. All right, this is tricky, or not tricky, but this tells us a lot. First of all, it tells us that my answer's not going to be that accurate. And what do you think when it says find one approximation? What does that mean in terms of answers? There are many answers that we could put here. Okay, so let's go back up and let's see what they're talking about. Find one approximation for the acceleration at one time. What does one time tell me we're talking about here?
IROC.
IROC, instantaneous, which means we're really talking about tangent line, which means that if I can find the derivative, I should. There's one problem. We have no equation to find the derivative of. This is why it says approximation. If we had been given an equation, we would have just found the derivative, v prime, and we would plug 40 in. But we can't do that here. So we got to do an approximation. So we've got to do the next best thing to tangent line. We've got to make our secant line look as close to our tangent line as possible. Remember at the very beginning of the year where we had 2 points? And we said, this is okay, but the closer they get together, that's going to be more and more and more and more accurate. So what's the best I could do here? What do you think? I'll give you a hint. I can't do this with 1 point. I'm not given an equation. What do you think?
Would you take the AROC of the 2 points?
With these?
Yeah, and then try to
Yeah, so we're going to do the best that we can. We're going to do average rate of change again. Average rate of change, but pick the 2 closest points that we can. You could, and this is why it says one approximation, we could have probably picked 1 point and the actual point at t equals 40. We could have done it here or there. All right, I'm going to pick the point one to the left, one to the right. And there are different ways to do this, okay? And so our answer for C is going to be V of 45 minus V of 35 over 45 minus 35. Okay, V of 45, I think I have this part memorized, 60, oh yeah, 60 minus 81 over 10, and this ends up being negative 2.1. It doesn't make sense that at time 40, we have a negative acceleration. Yeah, what are we doing in our car at time 40? Yeah, we're slowing down, we're decelerating. So it makes sense that it's a negative. Okay? So we're going to write it out again. We're going to say acceleration is, say, approximately or about negative 2.1 feet per second squared. And we cannot leave it here. We have to say when or where is this happening. So we actually have to use the t. If they give you a t value, you need to put t in your answer. When t equals 40 seconds.
Oh, okay.
Okay? All right, all of this is stuff we've done before this chapter. Okay? D, though, is this chapter. Before today, I have not shown you really this notation. All right? When you see this, you need to think, we're integrating. Now, if we were given an equation, we could probably do the integral like the real way, the true way. I'm going to show you all that next week. But this says with a Riemann sum. All right, now, remember we have options here. We have trapezoid, we have left rectangle, right rectangle, average the two, and we have midpoint. So they're going to give you some clue as to which one, and they do. They say the midpoints of 5 subintervals. And it says, using correct units, explain the meaning of this interval. Okay, so how long is each interval going to be if we have 5 total subintervals, or 5 rectangles?
2 boxes.
2 boxes, okay? So here's 1, here's 2, here's 3, 4, 5. Okay? We could also think of it this way. 0 to 10, 10 to 20, 20 to 30, 30 to 40, and so on. It's important that you note that these midpoints should be obvious, okay? If every box was 2 numbers, we wouldn't even know the midpoint. So anytime you're talking about midpoint, it should be obvious what you're dealing with. Okay? These are all 10s. So I'm going to encourage you on this one. I'm going to have you finish it here on your own. But I'm going to encourage you not to draw all your rectangles. I just want to see if you can do this. So go ahead and see if you can finish this one on your own. Come up with an answer and put your units, explain the meaning. Just go ahead and try to finish this part. Okay, if you're feeling stuck on this one thing to do here would be to circle your midpoints. These are going to be the heights of all of your rectangles. If you're feeling stuck. Or if you already are doing it, you should be using those numbers. Each rectangle is going to be, one dimension is going to be 10, one dimension is going to be 12. And if this is like overly confusing to you, well then you're going to have to go through and do and draw it out. I wanted to encourage you to try this without because you're not always given the picture. I'm trying to find the area of these 5 rectangles. If you're still not done, you're working too hard for your answer. Or you forgot your calculator. What'd you get for your answer?
530.
2530? That? Alright, what are my units? Feet. Okay, there's 2 ways you know this. One is we're going backwards in the derivative chain, right? Velocity is the rate of change, feet per second. We're going backwards, it should just be feet. It's not a rate anymore. The other thing is, to get this, we had to multiply feet per second times seconds. The seconds would cancel. That's another way you know it's feet. Once you know your units, then the meaning should be obvious. What's the meaning? It's the total distance. Total distance traveled. Is 25, 30 feet. And how long did it take you to do this?
50 seconds.
Yeah, so after 50 seconds. Okay. All right.